Curvilinear coordinate systems. Depending on the geometry of the problem, it may be preferable to work in a coordinate system other than the Cartesian coordinate system, which is our XYZ, to capture the natural symmetry of the problem. For example, if you think about the electric field due to a point charge, which is located at the origin 0, 0, 0, in Cartesian coordinates, we can write the electric field as Q, the charge Q divided by 4 pi epsilon 0 permittivity of free space x Ex hat plus y Ey hat plus z Ez hat. So xyz is the position where we're trying to calculate the electric field, divided by x squared plus y squared plus z squared to the power 3 over 2. Now you can see this is not a very practical way of writing this electric field. So instead of doing that, we can also write this electric field using spherical coordinates as q divided by 4 pi epsilon 0. It is in er hat direction divided by r square. So that's the magnitude of the position vector square. Now you can see this captures the symmetry of the problem a lot better. Therefore, it's preferable to use the spherical coordinates. Now, what are these spherical coordinates? They are r, the radial position, theta, the polar angle, and phi, the azimuthal angle, which have corresponding orthonormal unit vectors er hat, e theta hat, and e phi hat. But the difference between this set of unit vectors and ex hat, ey hat, and ez hat is that they are position dependent. Similarly, depending on the symmetry of the problem, we could use cylindrical coordinates, which are rho, phi, and z. Rho is the radial position, phi is the polar angle, and z is the height. So we have e rho hat, e phi hat, and ez hat, the orthonormal position-dependent unit vectors in this case. So these spherical coordinates and cylindrical coordinates, where we have orthonormal unit vectors but they are position dependent, belong to the family of generalized curvilinear coordinate systems, which is the subject of our discussion currently. Okay, so let's start talking about the position vector. The position vector r of p is a vector that points from the origin of a coordinate system to a point P. So this is our position vector. This is the origin, and we have the point P here, and we draw a vector from the origin of this coordinate system to that point P. The magnitude of r of P is the distance between the origin and point P, so that's this distance. And in curvilinear coordinate systems, since the basis vectors are position dependent, it may be preferable to draw the position vector and the basis vectors from point P. So because we have these unit vectors, orthonormal unit vectors E1 hat and E2 hat, they are not the same as what they are at the origin, so they are position dependent. Therefore, it may be preferable to translate this position vector here, so we can show the position vector and the projections onto the orthonormal unit vectors. Okay, so what is the position vector in the Cartesian coordinate system? It is Ri Ei hat, or we can write it as Xi Ei hat. This is the position vector, where we have the component R1 on the first unit vector Ex hat is x1. The component on R2, component R2 is x2, which is on Ey hat, and R3 is x3, which is the component r and on the z-axis. So these are the Cartesian coordinates. And note that Ri is equal to ei hat dot product with the position vector in any orthogonal coordinate system. Okay, so we can find that, for example, in a spherical coordinate system, we can find r theta to be e theta hat dot product with the position vector. Okay, so we have talked about an introduction to curvilinear coordinate systems. So depending on the symmetry of the problem, we prefer to use sometimes coordinate systems other than the Cartesian coordinate system. Electric field calculation for a point charge at the origin is a good example. The spherical coordinates capture the symmetry of the problem. So that the electric field is q over 4 pi epsilon 0 er hat over r square, where r theta and phi are the spherical coordinates with the corresponding orthonormal unit vectors er hat, e theta hat, e phi hat, which are position dependent. Similarly, in cylindrical coordinates rho, phi, and z, we have e rho hat, e phi hat, e z hat, orthonormal but position dependent unit vectors. So they depend on the point where we consider the position vector. So these spherical and cylindrical coordinates belong to the generalized curvilinear coordinate systems, and the position vector is defined as the vector that points from the origin of that coordinate system to the point of interest, with its magnitude being the distance to the origin. And because in curvilinear coordinate systems the unit vectors are position dependent, it may be preferable to translate it to point P to show the projections onto the basis vectors. And in Cartesian coordinate system, the position vector is Ri ei hat, which is xi ei hat, x1, x2, x3 being the components, which are x, y, and z. That's what we normally use in our discussion as the Cartesian coordinates. But for the position vector components in any generalized curvilinear coordinate system, we have ei hat dot r giving us the component, the corresponding component or the projection onto that unit vector.